Bismillah ar-Rahman ar-Rahim. Let's start on lecture 5. Basically, we're going to start with discussion of any further questions you have on assignment 1. Hopefully, all of you are done with it by now, but actually, so far, none of you submitted this assignment. So basically, I'm just gonna go over it or ask you for any questions you might have on assignment 1. We're going to finish the parts that we didn't cover last time. We're going to talk about quantitative estimation of performance, how to basically come up with a quantitative metric so that we can use it to estimate the performance rather than just looking at the waveforms. Because sometimes the waveforms are very complicated. Basically, we have the ECG here. We know how it looks like. But if we consider something like EEG or something like that, it's very complicated. It's very difficult to, for engineers at least, to be able to determine whether it's okay or not. So basically, we need to have a quantitative measure so that we can rely on and basically use to improve or optimize the filtration process. We're going to talk about the muscle artifact experiments. We're going to basically go over the remaining two types of artifacts, the muscle artifact and the electrode motion artifact. And basically, we're just gonna do a few experiments, and I will leave the rest of the experiments for you to finish in research problem 1 submission. But at least I'm going to just show you how you should proceed and how you should basically design your experiment so that you can cover these parts. I'm going to talk to you about research problem 1, what you're going to be submitting. I'm going to actually post a formal document asking you for exactly what you should submit. In order for things to be easier for you, I'm going to basically consider the first part, the assignment, as a part of the research problem 1 requirements. So basically, I'm going to ask you for a few more things, and this will be it. Okay, for the research problem 1. And I would like to also review the reporting of research results. So basically, you're going to do some experiments. I just want to go over a few basics of how to report research results. Okay, let's start first with the whether you have any questions on assignment 1. If you have any questions on assignment 1, please go ahead and do that. Go ahead and ask now.
Yeah, doctor.
Yeah, go ahead, Reno.
I asked you before at the WhatsApp. So currently I working on the number 3, which is how to reduce the noise of the EMG and motion artifact.
Actually, you're not required to do that here. You're not required to do that here. You're just basically you're computing and displaying the discrete Fourier transformation of the original ECG signals. That's it. Okay, here it's basically you compute and display. Okay, here you compute and display also the Fourier transform of the noise signals for baseline. Basically, it's just the difference between the original and the signal with noise. We're just computing and displaying. Here you determine the frequency resolution and bandwidth for the frequency spectra, which is basically one of the basics that we talked about in the Fourier transform. It's the delta F, and the bandwidth is basically equal to the sampling frequency. That's it.
FS, is it? The bandwidth is the FS?
Yes, yes.
And the frequency resolution is FS divided by NS. Is it true?
Yes, right. That's correct.
Okay. So I don't need to make a filter of the
No,
noise.
actually, this will be done in the remaining part of research problem 1. Okay. So basically, you're going to do that for, the upcoming or the rest of research problem 1.
Okay.
Any other questions? So if you don't have questions, I'm surprised that you didn't submit. Do you have any problems in finishing this assignment? If you have any problems, just let me know. because basically after today is the last lecture. Hopefully, if we finish all the topics that I listed, it will be the last lecture on this topic, on the research problem 1. So hopefully next week we're going to introduce, I'm not going to work on research problem 2, but I'm going to explain it to you, just give you the motivation for it and some general guidelines. And then in 2 weeks, after 2 weeks, we're going to go through the details of how to solve research problem 2. But basically, it should be the last lecture on research problem 1. So hopefully you will be able to submit not only assignment 1, but also the remaining part of research problem 1 in 2 weeks. So that when we start the research problem 2, you basically follow me on research problem 2. Basically, if you didn't finish research problem 1 and we got started on experiments in research problem 2, probably you're not going to be able to follow. So will you have any problem submitting both the assignment 1 and the rest of research problem 1 by the time we start the experiments in 2 weeks?
Okay, Doctor, after 2 weeks.
Yes. So basically, the deadline will be basically before the lecture, the Friday lecture in 2 weeks. So it's basically going to be the 23rd, October 23rd. Would that be okay for everybody?
Okay, Doctor.
How about the others?
Yes, it is okay, Doctor.
Okay, Doctor.
Okay, if you have any problems, please don't wait until the end of these 2 weeks. Let me know within this coming week or the following week, so that I can help you do, basically answer any questions you might have. Okay, if you need explaining, okay, if you need anything to be explained, yes, go ahead.
If you don't mind, about search problem 1.
Yes.
Okay, I think it's not exactly codes, right?
Actually, it's going to be experiments. So basically, you're going to do similar things to these, the things that you did here, but for the other 2 types.
Okay.
Okay. But it's not basically, the simulation part will not be involved, basically. So basically, it's going to be very similar to this part here. And I'm going to have basically this part here is just going to be for motion artifacts and EMG artifact. And basically, there will be a question that will be worth 20% of the grade of the second part of research problem 1, so the assignment 2, okay? That will be basically where I give you a signal with unknown noise. So basically, I'm going to generate a new signal, okay, that you didn't see before, and I will ask you to try to improve the quality or remove the noise in this signal, so that I can basically test how you understood the material and how you can apply it to something you didn't see before. Okay, so basically a question like this will be worth 80%, and other question where I have another signal, a new signal, will be worth 20%. Okay. So basically, for the remaining part of research problem 1 is going to be about 20 marks. So you will have 16 marks on the experiments that are similar to what I'm going to show you today. And basically, the remaining part, the remaining 4 points, 4 marks, will be basically on the new signal. Okay? And partial credit is definitely there. So basically, if you get a part of the signal, if you get a part of the question right, or tried in a direction that wasn't correct but makes sense, you will basically get almost the whole 4 marks. So basically, I want you to get used to working on open problems that they didn't see before, and try to basically propose ideas that make sense. I'm not asking you, I will not ask you to get things perfectly. Okay, as long as you went in a direction that makes sense, this would be enough for me. Okay, So don't worry about the grades. Just do your best and you'll be fine. Okay?
Okay, Doctor.
Okay.
Problem 1, 20 marks, right?
Yeah, the second part of problem 1. Basically, you have this assignment. This assignment is for 15 marks. Okay? As I said here, this is 15 marks. Okay? There is another 20 marks on the remaining part of it. So I will have another assignment that looks like this with the details of the things that I'm asking you to do. Okay, so that it becomes clear to you. Sometimes when I tell you, please filter this EMG noise in the ECG signal, you don't really know what exactly I need you to do. Okay, so when I put it like this, basically you have certain things that I ask you to do. It should be actually easier for you to follow. And if you have any questions, I can actually either modify this or add things so that you can know exactly or clearly what you should be doing. Okay. I need you to do whenever you get into this second part, we will see that these two problems are open problems, meaning that they do not have clear-cut solutions, meaning that it's basically a matter of the real world. Basically, you see things in the lab or in basically like some of the problems that we saw. You can actually get things almost perfect at the end. Okay, in these two problems, they are actually more like real world problems where you actually can do things, but you have trade-offs. You can improve something and basically make another thing basically a little bit worse. So I would like you to basically get used to this, okay? And basically do experiments, because experiments are basically, the research is just experiments, okay, of this kind. So I would like to see how you will do this. If you do the experiments and you have a logic behind the experiments, you're trying to remove something, you basically look at the artifact and you think that it should have this or the noise characteristics are so and so, and basically design a filter that matches whatever you're thinking. This should be enough for me. Okay, so for example, if I look at a signal and basically maybe I can just run the ECG demo, because usually we're going to start with this every time. So for example, if I see something that looks like this, okay, this is one of the signals, okay, and the noise looks like this, okay. So if I see something that looks like this and you saw some variations here, basically not just the high frequency variation, you see some low frequency variations, and you design a filter to remove these, not the high frequency, I would consider that to be okay. Okay, so you don't have to match exactly what I'm thinking. Okay, and basically when you're doing research, inshallah, in your thesis, basically nobody expects you to come up with something in particular. You basically try something that you think makes sense and make a case for it. You just put a good rationale for it. You basically explain to people or convince people that what you're doing makes sense. That's it. Okay? You don't have to go or reach a particular solution of a particular type so that your work would be accepted. So basically just do experiments, but have a rationale, a good rationale that makes sense, that seems correct. Like for example, instead of talking about the high frequency here, I talk about the low frequency variations here, okay? That makes sense, okay? Once you do that, this is step number one. Step number two is to implement the right filter for what you thought. So for example, if I have something that has variations that look like this, would you consider these variations to be low frequency or high frequency? The baseline variations here, will they be high frequency or low frequency? You see what I'm talking about? Such variations, not the very small variations here. No, I'm talking about the global variations like these. Are these high frequency or low frequency? I'm talking about low frequency or high frequency compared to ECG at least. Can you answer?
It's high frequency.
These are high frequency? See here, I'm not talking about the EMG artifact. I'm talking about the variations. See the variations here. You have a baseline variation here. The baseline variation here, if you look at it, basically it goes up and down, and basically in each one of them, there are several ECG signals. So it's definitely these variations are slower than the ECG.
Yeah.
So basically, if you come up with something that looks like this, and say that I'm going to choose a high pass filter, that makes sense. You get a perfect degree, get perfect score. Okay. If you design a different filter, then you didn't understand what you're talking about. Okay. So basically, you have a case, you have a hypothesis. Okay. And basically, you act upon it correctly. If I have a low frequency noise, then I have to have high pass filter. If I have high frequency noise, then I have to have a low pass filter, so on, okay, and so on. Okay, so basically, just going in the right direction after you chose your hypothesis, this will be very crucial. This is the one thing that does not allow ideas. Basically, it doesn't have opinions there, because once I say that the noise is low frequency, basically the only thing you should do is just have a high pass filter. Otherwise, you don't understand what kind of noise you have and how to remove it. Okay, so we'll talk about this at the end of the lecture. But let's now start with the part about the quantitative comparison of signals. Okay, so assume that we have two signals. One of them is the true signal, and one of them is the estimated signal. Now we're talking about, for our problem, we're talking about the reference signal. Let's just show an example here. This is, for example, the original signal, and this is the one with the electrode motion. This is basically the one that has the difference, okay? So this is the original signal, okay? And basically, when you were talking about the original, if you remember from last time, we tried to use, at least for the baseline wonder, we had some estimates for the recovery signal, basically. I took the signal with noise and passed it through, I think let's just go to the one that we used. We passed the signal through a filter, and it came out very close to what we had here, okay? So basically, how can we compare them to come up with a figure, with just a number? And this number would tell us that we are this much close to basically to the original signal, how much the signal improved after this filter. So the idea, or most people use something called the root mean square error. Basically, it's just the difference between the estimate and the original or the reference signal, the signal you would like your filtered signal to look like. And basically, you take this the mean of the square of this signal, and basically the square of the square root of the mean of the square of the signal. Okay, why do we do that? Basically, the idea is because we have the noise can be positive or negative. So let's try a particular example. Let's try a new code here, just to show you why we chose to go this way. In here, I'm going to basically simulate a signal with noise. So basically, let's start with a part of the, as we do every time, we'll just take a part of this, take whatever signal we want from here. I think this is not necessary here. So basically, I'm just gonna take this as an example. Oh, sorry, I have to take all of them. start with any signal. Just I need the regular. Maybe you can just try with a regular signal, any sinusoidal signal or something like that. So basically, we'll say that n capital is equal to, or n samples is equal to 1,000, for example, 100. And basically, we're just going to simulate a signal with frequency f node equal to, for this here, maybe 10 hertz. So I'm going to generate maybe n small is equal to from 0 to ns minus 1. And maybe x is equal to the signal is equal to sine of twice pi times f node times t, which is basically, let's maybe put here t node equal to 1 over f node times t, okay, times n, and just plot it. So there's something wrong here. Okay. Maybe it's okay. It's undersampled. Okay. Let me just close everything. Here we have the steps. Here will be from 0 to 100, and we have a frequency of time twice pi. So basically, I would like to have at least 10 samples every F node. Here will be maybe 10 samples. Just put that as 1 hertz. Obviously, something is terribly wrong here. Okay. Oh, okay. F naught is different here. I'm sorry. The sampling frequency is different. I put this wrong actually. I just put the sampling frequency as F naught here is 10. The sampling T naught is 1. Maybe this is the sampling frequency. Yes. Maybe we'll put it as 0.41. It should work. Basically, this is what we did in the simulation before. Okay. It doesn't look that good. Let's probably make it 5 here so that we can see it clearly. It's okay. So basically, we're going to add some noise to this signal. So basically, I'm going to have X estimate equal to the same signal, same exact signal X plus noise. In order for us to generate noise, there is a function called rand n in MATLAB. And this rand n generates a normal distributed random noise. Okay. All you have to do is just use rand n and put the array size, basically. Okay. So basically, if I wanted to have an array of 100 by 1, I just write 100 by 1. That's it. And it generates noise that is basically, it has a mean of 0 and standard deviation of 1. Let's just try it. I'm just going to add it here. Just want to make sure first that the size of the signal is 1 by 100. So it's 100. Okay. Let's try to see it. Maybe I can plot the two together. So I'm going to, so that because the noise actually has a wider range. So what I'm going to do is plot X estimate first. And then hold on. And then plot X. And then hold off. And maybe you can plot it with reds. Okay. Of course, the noise here is extreme, basically, because you have a very high noise here. It's much higher almost than the amplitude here. Basic amplitude here is 1. And if you have a standard deviation of 1 for a random noise, the values of the random noise will basically go from -3 sigma to +3 sigma. So if you have a standard deviation of 1, then you will end up having variations from -3 to 3. See here, some things went up to 4 or higher than 4 here. Some things went close to -3. So probably we should make the noise a little bit smaller so that it can be realistic, more realistic. So I'll just put it 0.1 times this. It looks noisy, but actually let's try it. It looks a little bit noisy, yes, but it's okay. Maybe this is a good example to show. So now you see now the signal with noise and the original signal. Okay, basically if I took the difference between the two, okay, so I'll have figure 2, and I'll plot the difference, x estimate minus x. And I'm going to plot, for the second one, I'm going to plot the same exact equation that we saw here. So x estimate minus x, basically if you want to have all the individual elements in the array raised to the power or operated on by this operator, you have to use the dot here, dot operator here. Okay, if you just use, if you have a matrix or an array here and just use the power, basically to consider it as if you're multiplying this by itself. And if you have a vector, it will not be able to do that. If you have a vector that is n by 1 and you multiply by another vector that is n by 1, it will not match. Basically, you have to have the inner dimensions basically equal to each other. Okay, so when you use a dot operator in MATLAB, as you know, you basically apply this operator to each individual elements here. Okay, so let's just put it here this way, exact same way. Let's see the difference between these two. What is the difference between these two, in your opinion? They look different, right? What is the main difference between this one and that one?
It's positive.
Yes, here you have positive and negative. Here it's all positive. Basically, if you go to your code here and basically if you just add them together, add these numbers together, just gonna add this first. And I'm going to add this one here, square. Okay. Let's see the difference between the two sums. The first one came out negative, which doesn't make sense actually. What's the meaning of a negative error? And the problem is basically when you do that, sometimes you cancel out, things cancel out, okay? So basically if you have something that is square, you come up with something that would be actually more reliable. So it will count the negative error as much as the positive error, okay? So basically in order for us to see that more clearly, if I actually go to my code here and add another one, another item, I'm just going to add the absolute value of this. The absolute value, basically, if you have a positive or negative, it will basically turn it to positive. So basically, the difference between these two, see here, Basically, of course, each time it will be different because when you're trying to use random numbers in MATLAB, it will regenerate each time random numbers. So here, as you see, the error that was just coming from the summation was much smaller than the error of the absolute values, meaning that many of the errors actually canceled out. You have a positive 1 error and a negative 1 error. When you add them together, you'll basically see the signal as if you don't have any error, because basically +1 -1 is 0. Okay, so this is a problem. Some people use this absolute value. Some people use this mean square, okay, or basically the summation of the square errors. Okay, if you basically divide this number by the number of elements or the number of points in your array, you get the mean of the error, basically. Okay, so people prefer to use mean square error because basically it has been used for many applications before. Okay, but actually the idea of using the absolute value is actually has been used in several applications. So let me give you the generalized form for any calculation like this. So basically, if you have something that looks like you have x and x estimate, okay, each one of these is just an array. Okay. Basically, if you remember from geometry or linear algebra, each one of these is like a vector. This is a vector, and this is a vector. Okay, so what you're doing here is you're trying to see the error vector between these two. So basically, if you're talking about two-dimensional vectors, basically if you have something that looks like this and something that looks like this, you're computing something that looks like this. This is the error. Okay, and then when you're trying to basically get a measure, you can actually measure the length of this vector as the basically indication of the error, because sometimes it doesn't make sense to get the difference. If I just take this minus this and it came out a vector like this, sometimes I can't make sense out of it. Basically, if you have a signal that has 1,000 points, if I give you the difference in each one of the 1,000 points, it's extremely difficult to compare these errors between different techniques. So we'd like to reduce that to single number. And the best way to do that is just get the length. How do you get the length of a vector? Do you remember? If you have a vector, for example, if you have 1 and 2, this is a vector. How can we get the length of this?
Using Pythagoras.
Yeah, Pythagorean equation, right? It's just like basically 1 square is a plus 2 square, and basically it's going to come up like square root of 5, right? This is what you're used to, right? We have been doing that for, you know, at least in the geometry for a while. Basically, this is the most common one used, actually. Basically, there is a generalization of that. Okay, first of all, length in linear algebra is basically termed norm. Have you heard of this term before? The norm of a vector? This is a generalization of the length in general. Basically, length in general can be computed using a norm. And this norm actually has the Pythagoras equation here, basically, as a special case. So the norm actually is computed like this. Basically, what you should do is summation. If you have your vector x, for example, and the elements of x are xi, you compute xi absolute value to the power n and take the square root n, and this will be called n norm. Just consider the special case when you have n equal to 2. So basically, the very special case of this, it will come out like this: square root of 2, which is the usual, summation of xi square, which is exactly what we did here. Okay, summation over all elements. So basically, in the special case, it goes back to Pythagoras. There is one norm, basically the new norms that I'm going to tell you about. There is one norm, and sometimes it's very useful to use the one norm. You will see it in papers at least. Basically, you can compute the length as basically equal to square root 1. Actually, the square root 1 is just no square root. You don't really need to even put it. So basically, it's just a summation of absolute value of xi. That's it, to the power 1, which is basically exactly the same. So this is basically exactly the same as the summation of absolute values. Okay, so this is a very special case. Okay, sometimes you hear about something called infinity norm. Okay, so basically infinity norm by definition will be basically, if you use this equation, if you have a summation here, if you have elements here raised to a very large power. Imagine that if you have two elements, one is equal to 1 and one is equal to 2, the same exact vector that we were talking about here. I have 1 to the power, for example, let's just put it as an example here. You have a vector that looks like this, basically 1 and 2. If you have 1 to the power infinity, to be what?
1.
1. If you have 2 to the power infinity, it will be what?
Infinity.
Infinity. So basically, if you have one single element, basically the largest one will be dominant. So even if you have a very small difference, with the power, with the infinity power that you have, basically the maximum value will be dominant. And anything else will be basically negligible with respect to the maximum value. So basically the infinity norm is just the maximum value. Okay? So basically, sometimes you hear about techniques called min-max. I'm not sure if you heard about that or not. The min-max, basically, if you have an error, you're trying to minimize that error. Okay, so instead of trying to minimize the distance or basically the distance that we're talking about as a Pythagoras equation, I'm trying to minimize the maximum error. So this is a min-max approach. So for example, if you're trying to do your experiments and you basically had two filters and you compute the error for first one using the Pythagoras equation, and it was like 5. And you have another technique that has an error of 3. Which one would be better? The one with the least error, right? So basically, if you're using Pythagoras equation, then you're basically minimizing the error as defined by the two norm. But sometimes it's better, in some problems, it's better to minimize the maximum error. Meaning that if you have a vector with very long, it basically has very long length, basically instead of trying to minimize the summation of the errors in all of the points, no, I'm going to see which one has the maximum and minimize it. Okay, so if I tell you that the min-max error, okay, was this value, okay, if the min-max error is, for example, 1, this means that in any one of the points in this array, the maximum error you would expect is this value. Sometimes it's very useful to do that. Okay, so basically I'm just showing you basically the definition of norm is really important that you know. Okay, so basically I want you to learn the definition of norm because you will see it in papers. This is basically vector norm. It has to be a vector, okay? So basically you'll see it in paper. Sometimes you see that they basically minimize this, okay? So this is okay also. You can also choose to do this instead of doing the Pythagorean equation, just getting the difference between the signals and then computing the basically the summation of the squares and then taking the square root. You can just add the absolute values. It's acceptable, definitely acceptable, okay? Some of the new techniques actually found that if you use a norm that is different from the 2 norm, the regular 2 norm, which is basically the length, the regular length that we use, basically sometimes it has advantages, okay? So there is a function actually in MATLAB that you can also try that computes the norm. So basically you can compute this equation instead of writing that yourself. You can just use norm. I think it's a norm. At least last time I used it, it was norm. It's right there, okay? So basically I can compute this value, the same exact value, instead of saying sum of this minus this and so on, or basically taking this and then taking the square root after that, I can just compute the norm. So basically if I compute norm of x estimate minus x, and 2, it will give me basically the 2 norm. Okay, this is a 2 norm. Maybe I can just put several ones. We put the 1, the 2, and the infinity. I'm not sure you write infinity, I think, as INF. Let's see. P is the norm. Yes, it's INF. Okay. If you basically minus infinity, it's basically you're talking about the smallest one. You get the minimum. Okay. So basically, I'll just put it here as nth and see the 2 values. So basically, this computes whatever the equation tells you. So basically, you have the definitions here if you want. Basically, the definition is maximum of summation of this, but this is for matrix. But actually, if you have a vector, it will be just the summation of the absolute values, okay, and so on. So let's try it. Here, see, this is the 1 norm, this is the 2 norm, this is the infinity norm, okay? You can rely on any one of these. It's up to you. Basically, at least in this project, you can try any one of these norms as they are all acceptable performance measures. If you use 1 norm, 2 norm, infinity norm, any norm you want, it's fine. Okay? Do you understand the definition of norm? Okay. So if you have any questions, we can discuss it also again. No problem. By the way, if you have any questions, and basically if you, for example, you're the only one of the class in the class that you didn't understand a particular part, you can actually ask me for office hours. The office hours, you don't have to come. You can basically let me know and we can arrange a time, and basically it's going to be a Zoom meeting. Okay, so if you have any questions, we can arrange office hours so that I can explain the particular things that you want me to explain to you. So I'm going to go back here, and basically the thing I wanted to tell you about, there are some problems here when we try to do quantitative estimation of performance. Let me show you an example from the things that we did before. Maybe try that. Any one of these examples should be okay. Maybe you should try something with baseline wonder. It doesn't matter. Go ahead. This one should be okay. So I'll run that to remind you, this is what we got last time. I think probably this doesn't look that good, but actually this is the one with zero phase filtration. This doesn't look very good actually. Maybe I can, okay, we changed that F pass and F stop. Maybe you can return them back. F stop 25 is okay. This is 1, should be okay. Try that. Yes, that looks okay. So now we have the filtered signal. For example, this is the filtered signal. This one here is the filtered signal. Do you see any problems when we try to basically subtract this signal and that signal? Would it be okay to just subtract these two and compare it directly to another one? Basically, there are several problems. First of all, the transient here is a big problem, because you know that the transient will be there. If you use a filter, a regular filter, not a zero phase filter, you have a problem. You definitely have a problem, because basically the first part of the signal, you know that it will never be exactly the same. It's a transient period. So basically this is a major problem. The other thing is sometimes the original is a little bit different from the filtered. Even for the zero phase, compare this one to that one. You see here some slight variations that are acceptable for the user, okay? But actually ours here is a little bit better. But actually, if you try to get the difference between these two, you will find that basically you have a difference that is significant. So basically you're penalized, you have a penalty in the subtraction that is basically, you have a better signal than the original basically. And you know, how much you're better than the original will be basically counted as an error, which is not good. So basically you have a problem like this. There are other problems related to basically, so basically if you have a transient, it would be a problem. If you have a gain, sometimes basically, as we said that in the passband, sometimes we allow the passband gain to have a certain range here, this value here, the pass here, this value here, okay? So if you have a gain here, let me try to change it a little bit. Maybe if I can have it as 0.5, basically, you will see a big difference between here and there, basically. The gain will actually cause you a problem. Let me return it back. So basically, if you look at the level here is at 0, because basically we remove the DC value of the original. Whenever we have a high pass filter, it would remove the DC value. DC value is the offset. So instead of having a signal that goes around 800 here, it's going around 0 here. This is a big problem. So basically in each one of the points here, you have an error of 800. So regardless, if you look at the magnitude of the error, the magnitude of the actual baseline wonder, it's much smaller than the 800. So if you count that, this would be a big problem. So before you just blindly subtract the two signals and try to estimate the error, you have to look at the two signals and try to take care of these slight things. So for example here, you probably want to remove the DC value here. You just subtract the average of this here, so that when you basically compare it to the outcome of the filter, basically it makes sense. Otherwise it won't make sense. Okay, so sometimes basically because of these issues here, okay, if you have basically if you have a transient, basically you have to start after the transient. So if you have a transient here, if you want to compute the error, you cannot start computing the error from here. You should actually remove the first part of the signal. Okay, you should remove this. Okay, do you know how to remove a part of an array? Let me show it to you. No, remove a part. Basically, I have an array that looks like this. Basically, I want to remove this part here. No, not just basically I have these numbers. I just want to remove the first 100 points, for example. How do you do that in an array? So basically here, I don't want to see this. Okay? How do I do that? Okay, let me show it to you. Okay, so basically here I'm plotting sig f. Okay, I'm going to do something here sig f. Here the order is basically I have all the values here. The order is 602. So I expect the transient to start to basically have 301 points, right? It's basically the number of samples where the transient will be present. So basically I'm going to take that sig f from 1 to n over 2 and make it equal to nothing. Let me show it to you here first, and then maybe I'll say z is equal to 1 to 10. Okay, array from 1 to 10. Okay, if I say z of 1 to 4 is equal to nothing like this, see what happened? So whenever you equate a part of an array with an empty array, it will basically remove it from your array. Let me show you here what I can use that for. So basically, if I just did this step and basically remove these elements before I displayed my my array, let me show you how it would look like. Okay, it still has some noise here, but actually maybe the noise is a little bit higher. But actually, if you see, basically this peak is correct actually, but this one is still not correct. So at least if you want to remove a little bit more, maybe maybe I can just basically consider the first n elements as basically noise or basically transient. Maybe I can just have it as from 1 to n. Okay. So that when I try to compare them, I actually get something that would make sense. I can compare it directly to the above ones. Basically, I have to do it, of course, to all of them. Okay, so I have to basically remove the first n elements or n points in the array from from this one and from the original one, so that I can subtract them. So basically, I can do that from there. The point is you have to also take care of the delay. You have a group delay between the outcome here and the input here. Okay, and this can be a problem. Okay, so basically if you have a group delay, then this will not coincide with the element above. Maybe I can show it to you if I remove this and show the original outcome. So for example, if you look at this here, you will see that basically if you compare this and that, for example, look at this here, this is at this point right there. If you look at where it went or where it appeared later on, okay, after the group delay. So basically, if you try to subtract these two together or subtract this one here from this one here, you will have a problem because of the mismatch. The outcome is a little bit shifted from the income. The input and the output of the filters are not synchronized together. The points are not matching each other. So you have to take care of that by shifting the array by the amount of the group delay. Okay, I think this will be a little bit difficult for you to do, but actually, so basically, I would suggest that you use something that has zero phase filtration, so that you can basically get rid of both the transient and the shift. So the use of zero phase filtration, okay, will give you an idea about how this filter is doing. So basically, if the zero phase filtered result gave you the minimum error, then use this filter in real time, it would be okay. Because it's exactly the same filter, but basically removing the transient and the group delay. Okay? You understand what I mean? I told you before that the regular filtration is useful for real-time filtration. If I wanted to implement a filter in an ECG device, then it has to be implemented as regular filtration, not zero-phase filtration. Zero-phase filtration would require you to have the whole signal before it actually can be applied to the signal. So basically, this filtration is the one that is practical. But actually, the results of the zero-phase filtration would give you a good idea whether this filter is good or not. Because if you try to match this to that, it's really a tedious process. I don't want you to get into this tedious process. So just use the zero-phase filter, and based on the error of the zero-phase filtration, you can basically conclude whether this filter is good or not. Okay, so compute the error from the zero-phase filtration, even though you might be using regular filtration in practice. Okay. Okay, so another problem, but this is not actually basically these things here. You might see some differences between them, but actually, basically the reference in particular is a very big problem, because usually what you have, if you look at these signals, you don't have an original signal. Basically, if you have an ECG device and it came, basically the signal from the ECG device came out like this, you don't have any idea how the original signal looks like. You don't have the original signal at all. So basically, how to estimate the original signal is a big problem. So sometimes it's basically the reference might not be even available. For research problem like this, you have a reference signal because you're using a database. But in reality, you might not have a reference signal. So basically, this is something that you have to basically think about or keep in mind. Okay, let me show you something here. Maybe I should just save this into another lecture 5. Okay. Basically, I'm going to plot the seq-f with the original in one figure, as we did before. I think we did that in another 5, but let's just draw it again here. So I'm going to plot the signal. Need that. And I'm going to plot the zero-phase filter signal on top of it. Just use the hold on and plot that. Okay, and maybe have it in color. Okay, maybe I should remove that. Okay, I plotted them together on the same plot here. Do you see a problem? We saw the problem of the shift, right? Let's remove the DC of this one here, so that we can at least basically have exactly the same signal. So I'm going to make sig equal to sig minus mean of sig. I'm just going to remove the mean value of the signal. That's it. Okay. Let's try that now. And when you compute the error, you have to do that. How do you like that? Is that a good match between the two? It's almost there. It's not very different. Okay, you see here in some parts, it's almost, they are overlapping completely. You have some, the error that I showed you before, the slight variations in the original signal is present there, but actually it's okay. In most of the ECG cycles, they are okay. If I go here and change that, the D-pass here, and make it a little bit higher, okay? Let's make it, for example, 0.1. You start seeing some separation here in some parts. This can be a problem. Okay, so basically, if you find that the you have variations here between the original and the zero phase filtered, you might want to come here and basically play around with the D pass here, the passband ripple. Because basically, if you have a passband ripple that is a little bit large, you might end up having some differences here that were not there. You might have some gain, basically, and this gain can affect the original signal. Okay, can affect the filtered signal. The filtered signal will come out a little bit different from the original. But actually, it should be okay because basically you're measuring the difference here, and basically you can do that very easily. So basically, if I wanted to compute the error now, I can go and take the code from here, see the norm here, and just take them and just place them here there. Okay, so basically I'll just say that this of error norms this of this. You can just display them in one array, just side by side. Just put them in one array and basically just going to display them right there. So basically, in addition to the things that we saw before, the filter order, the filter group delay, the transient, now I have an estimate of the error norms, as you see here. This is one norm, this is the two norm, this is the infinity norm. Okay, so now if I change things, if I change anything there in the parameters, for example, if I use the D stop to be, for example, whatever D stop, actually this should be okay, maybe 0.01, for example. Okay, now you have different values. Maybe it's actually didn't change by much. Actually, 0.78 actually didn't change by much, which is very surprising. Actually, it should change a little bit. Did we do anything incorrect here? Oh, okay. I'm sorry. I'm using X estimate and X. Okay, sorry. I have to use the difference between sig FF and sig. Okay, instead of X and X estimate. Okay, maybe we can do it this way. That we have the same terminology. X is equal to sig. Okay, so that can be a little bit clearer. So the error here is the first one here. The error norm is this multiplied by 10 to the power 5. It's very large because the array is really large, 10,000 points. Okay, so it looks like this. Let's try a different parameter. Maybe I can try the same setting that we used, maybe 0.1 here. So now the error is a little bit large here. See here, for example, compare this to this. This is 2.2, this is 2.4. So definitely this wasn't good. If I take the two norm was 0.033, this is 0.028. Okay, so definitely this is not a good answer. This is not a good solution. This is the one here was better, which makes sense because here actually this is the attenuation. This is the attenuation in the stop band. Now I have it as 1/10. Before I had it 1/100, which is actually better. I'm attenuating the artifact a little bit more. How about if you make it 1/1000? You can try it here. and you will see that the differences actually, you can compare the differences between the different ones. For the 1/1000, you notice that for the 2 norm, this is almost the same number as the one with 1/100, which means what? Which means that 1/100 is sufficient. See what I mean? So it's not, basically you're trying to do something based on engineering. Basically, you're not trying to do something perfectly. You're not trying to make the attenuation as 1/1 billion. No, you need to have the attenuation as large as sufficiently needed. Okay, as needed only. Okay, so as long as I tried 1/1000 and it gave me something that basically that is very similar to 1/100, then I can conclude that 1/100 is basically just as good. Okay, if you look at the error here, maybe you can just look at any one of them, but actually sometimes it's the 2 norm is the most common, but you can actually still compare this and this. You can actually, if even you compare the 1 norm here, okay, the 1 norm here is 2.2966. Here it's 2, for the one that didn't look good, it was the one that didn't look good, what was 2.42. Here it's 2.28. If I look only at the first digit here, this is 2.3. This is approximated at 2.3. This is also 2.3. This is 2.4. So basically 1/100 and 1/1000 are almost exactly the same. It's up to you to define basically the resolution or the decimals that you would look at. Okay, so if you look at the first decimal, then you're basically just as good. If you look at the second decimal, you're very close, but actually you might see some difference between the two. Okay, so this is a kind of thing that I would like you to do. Is that clear? Basically, you do that for all kinds of filters, by the way. Even if you have a frequency domain filter, you can still do that also. Because basically what you came up with the filter, let's try that also. Maybe lecture 4, frequency domain. Yes, this is probably it, or maybe this is it, yes. Let's try that here. I think this is the one. Okay, this is basically this is the one that we had, noisy versus filtered with the ECG. Okay, so basically you can do exactly the same thing. This is a spectrum in the same exact code. Just save it. Like 5. So basically I can just take the same exact code here. Same exact code, but actually it doesn't matter. Maybe I can take that one as well. So now SIG, I think I have SIG here. SIG is already there, I think. So it's already there. The signal baseline frequency, I think this is the one that that is filtered here. So it's SIG, and I'll use it here also. So is there any error here? There's no SIG here. I didn't use SIG here. Yes, it's right there. SIG is right there. SIG black and white. SIG N. This is the one with baseline wonder, or SIG is there. Okay. Maybe I remove the DC value here somewhere. Double of this. SIG BW. Okay. Let's move that. Okay, let's try it this way. Okay, looks like this. And you have the errors computed here also, like just exactly like the first one. So basically, the way you compute the error in all filtration methods, whether they are FIR, IIR, or frequency domain, it's exactly the same. You just basically put X estimate as the filtered signal. X is basically the original signal, and basically just compute the norm. That's it. You have the choice of which norm to use. Sometimes if you want to use, for example, if you want to try something different, you maybe try norm, third norm or something like that, it's fine, 3 norm. Okay, so basically it's up to you. Is it clear for you how to compute the error, how to basically get a performance measure?
Yes, doctor.
Okay. So now what we're going to do next basically is try a few experiments with muscle artifact and electrode motion artifact. I would like to just emphasize that both problems are open-ended problems. So what you're going to get is something that is less than perfect, definitely, okay? The important thing is to try to identify the kind of artifact that you have and try to deal with at least a part of it. I'll show you how right now. Before I do that, I would like to just discuss with you the problem with each one of them. Basically, what we have in this problem, basically for the muscle artifact and the electrode motion, okay? Basically, the filtration we have is, as we said before, is frequency, selective, process. Meaning that if I have a spectrum, okay, if you have a spectrum of any shape, if it looks like, for example, this, okay, I basically say that I have a good, basically a part here that is not good, and a part here that is basically good. I want to keep this, I want to remove that, okay? Each one of them is defined by a certain frequency range. Okay, this frequency range can be to the left, to the right, in the middle of the signal, it doesn't matter, but it's a particular frequency range. Okay, and we choose high pass, band pass, band stop, whatever, but actually it has to have a certain frequency range. Okay, if it happens that basically if I have a signal that has, for example, this is the true signal, and this is the noise. Then we have here a problem. What is the problem here? We have a problem that this is basically the frequency. We have an overlap between the noise frequencies and the true frequencies. If you have any frequency, for example, this one here, okay, if this frequency has signal from both the true and the noise signals, you cannot recover the true signal. It's as if you're saying that at this, basically, if I take the spectrum of this signal, if it's x of f, okay, is equal to x true of f plus noise of f, okay? The filtration, basically, if you try to filter the true signal from the noise signal, it's as if you're trying to solve a problem of 5 is equal to x plus y. You have one equation in two unknowns. You cannot estimate a unique solution for x true here. It's impossible. So frequency selective means that you have to compromise. You have to basically, for each frequency, you have to label this frequency either as true signal or as noise. You cannot label it as this and that, or a gray area. You don't have gray here. It's either black or white. It's either signal or noise. You cannot have both. So this is a big problem in, for example, in both actually, in these two types of artifacts. The EMG, by definition, you have frequencies from almost basically from the start, basically almost zero or a little bit higher than zero, okay, until maybe 1 kilohertz. So the EMG frequency range basically starts with same frequencies as ECG and can go all the way up to maybe a few kilohertz. Okay, so what can we do in this case? So basically, it's exactly what I was telling you now. The ECG range, if we basically say that the ECG starts from 0, this is 0, okay? The ECG will be like this. The EMG will be like this. Actually, maybe I should write it a little bit different. It's actually like this. It's much larger than ECG. Okay, so basically this is high frequency, this is low frequency, this is high frequency. That's why when you see the overlap, you can actually see that it actually has much higher frequency than ECG. But actually there's a part that has an overlap. What can we do in this case? How can we filter EMG out of ECG? Any ideas? Actually, it's very difficult, okay? And basically, you start seeing problems where you have trade-off. Okay, trade-off means what? Means that if you try to have, first of all, the EMG is high pass noise. Okay, or but let's just maybe instead of pass, because actually high frequency noise. If I can write it down altogether. Okay, meaning that you will need a low pass filter, definitely for your solution. Okay, the trade-off becomes in actually selection of cutoff frequency. Basically, if I make it extremely low or extremely high. If I make it low, this means what? You will remove much of the EMG signal. So remove more EMG, right? But you remove also more ECG. If you have it high, you remove less EMG, which basically makes the filter useless. So basically here, you need to have it low enough to remove most of the EMG signal without affecting the ECG signal. So basically the best you can do, as a conclusion of this, try to find a filter that satisfies the following. Okay, first of all, you're trying to filter the ECG to get a better ECG signal. So basically, you have to have satisfactory ECG signal. No distortion. Or basically, without saying distortion, basically you get as good as you can, as good ECG signal as you can, while removing as much EMG as possible. So basically you're trying to reduce, you start with a particular frequency and you try to reduce this frequency until you see a distortion in the ECG signal itself. Okay, let me show it to you. Maybe you can try that right now. We have to design in this case we have to design low pass filter. So basically you have to go to Filter Designer. Okay, filter design. Okay. So basically, I'm going to start a low pass filter, and if IR is okay, sampling frequency as we did before, 360. F-pass, let's start with 60 for 100, for example. F-stop, let's make it maybe 120. And the attenuation, let's make it something modest, like 40 decibels. Design. So it's a low-pass filter with a cutoff frequency of 100. As you see, the order is very modest. It's okay. It's nice. So let's generate the MATLAB code. Leg 5, EMG or MA, because it's muscle artifact. Low-pass filter 1. Let's write it FIR also. Okay. So now we have it here. We do exactly the same as we did before. And maybe I can take this here and let's just take these parts here. It's very useful. CM. Oh, actually, you can take all these. Copy them here. Instead of using the baseline wander here, I'm going to have the MA. Okay. Maybe we can take the norms also, so that we can compute everything. We can just take this as well. Actually, I don't need this. We can just compute the norms. Okay. So basically, we're doing everything that we did before exactly the same way, but instead of selecting the baseline wander here, it's just the EMG. We're going to actually use exactly the same filter also for the other type, for the third type. Okay, so let's try that. Okay, does it look okay to you? Let's compare this to that. It's very difficult to compare the filter because of the offset here. So basically, let's compare the zero phase filter. As you see here, we don't really need to remove the DC value because basically it's a low pass filter, so it keeps the DC value intact. Is this better than this? Let's see the values here. The values here are really really large. So it's a power 6. So what we should do is probably go here and try to make this f-pass a little bit smaller. Maybe I can make it 50 and make the f-stop at 60. Let's try that. Is that better? Sometimes it's very difficult to see basically the difference between the two. So basically, let's go back and use the values that we generated. Actually, it should be much better. Actually, if you compare, at least the first one here there's a very big difference between the two. Also, this is here, you see a big difference. Here, the difference was in probably the other decimals, but actually, if you look at the two node, there is definitely a difference. Okay, let's try to take it down a little bit more. So the signal here, maybe I should close all these. The outcome signal here still look like ECG. So basically, we didn't affect the ECG. If we take a little bit smaller, maybe just put it here as 40, and this one here as maybe 45 or something like that. Actually, it might look a little bit better. So some of the noise here looks a little bit less. ECG is still okay. Let's look at the difference here. This is 0.0105, which is actually definitely better than this one here. So we're going in the right direction. Let's keep doing that. I'm just gonna take that as 30, and this is like 35, and see. It looks better. Basically, look at this one here, for example, and compare it to this one here. You can see that this is actually, as I told you before, whenever you have high frequency noise, it would look like a thicker line. Actually, this is thicker than this here. So basically, we're improving now. Is ECG, do you see any distortion in the ECG signal itself? I actually still see the ECG signal okay. It doesn't really have any problems. The QRS, which has the high frequency in the ECG, still looks very sharp. Okay, let's try it a little bit further. 20, 25. How do you like that? Actually, it's much better than this one here. And surprisingly, the ECG looks okay. Okay, so if we take it a little bit further, which I don't expect it to work, but let's try it. Now you started seeing a distortion in the ECG signal itself. So now the ECG doesn't look right. This is not acceptable. So the previous results, basically here you don't see any high frequency noise. You see very clean, very thin lines that basically show you that you don't have any EMG artifact anymore. But having no artifact on a distorted signal is not useful. So you have to have the original signal exactly the same with a reduced artifact. Okay? If you take it a little bit further, you take it further than that, if you take it to the point where the ECG signal doesn't look like an ECG signal, then you will have a problem. Okay, so the previous result, the one that we had before, was actually not bad. It's okay, it looks okay. The ECG signal looks okay. The artifact here looks a little bit reduced. So basically, if you compare this to this, definitely it's reduced. The first 3 cycles here, definitely it's reduced. So this is a kind of optimization I want you to do. Do you understand how to do that? Any questions about how to do that? Do you know, basically you should try that exact same procedure with IIR and frequency domain. In all of them, basically we determine the cutoff frequency. Okay, so you keep changing the cutoff frequency as long as you determine that you would like to remove basically any frequency above a certain frequency. The design process, the optimization of the design basically is just a better selection of the cutoff frequency. Okay, so you keep changing the cutoff frequency. You look at the figures here, the figures of merit here, the norm, the error norms. Just choose one of them. You don't have to look at all of them, basically. And based on that, you tell me that I optimized the design, and this is the one I find to be basically the best design. How many experiments you should do? Actually, not many. I don't want you to stay for a day or something like that. If you keep doing that, basically, you can. It's open-ended, as you see. You can keep changing things. You can keep, maybe you can change and choose another type of FIR filter. If you go here to the filter designer, there are so many types of FIR filters. You can change the parameters here. You can basically change to IIR filter, change to a frequency domain filter. Basically, you have open-ended problem. And whenever you change, basically for this 20, maybe I can try 21, maybe I can try 19.5. Basically, after I finish or get the integer value of the frequency, should I go to the first decimal and the second decimal and the third decimal? No, I don't think so. Okay, so what I want you to do is do a reasonable number of experiments, maybe 3, 4, something like that, 5 maximum. Okay, and just report what you have. Just report your experiments, basically how many experiments and the results from each experiment, as you got them. That's it. Is it clear? Is that clear for all of you? Is it clear for all of you? Okay. Let's try now the same exact code here, and instead of having the motion artifacts, I'm going to put the other type, sorry, the electrode motion. So I'm just gonna, by the way, in each one of the signals here, you have signal number 1 and signal number 2. Maybe I can show it to you before I get into the other type. Here you have 2 signals for each one of the signal types. You have, first of all, you have S118, it's a patient, and S119 is a different patient. Okay, so basically I can have signal number 2 here. Okay, this is the second signal. Basically, ECG is not just one signal. Usually, if you're measuring the Eindhoven triangle, if you're measuring the basic leads, 1, 2, and 3, basically you compute only, you get 2 of them, and you can compute the third by just subtracting the 2 or adding the 2. Okay, so basically this one here, it's basically it's exactly it's a second signal. It looks a little bit different, and with this is not baseline wonder, of course. Maybe I should change that so that you didn't get confused. So you get a different signal here, and you get a different response here. So sometimes it's good to look at another signal, because sometimes for one particular signal, it's okay to use a filter with a particular specifications. But if you try it on another signal, it might look really bad, like this one here. It's exactly the same parameters, but actually it looks much worse. Okay. Actually, there's one here. Actually, okay, I'm sorry. Here you have to have the basic. I had here change something. If you maybe I put it here also, lead equal to 1 or 2. Maybe I should have a 2 and change that here to lead. Because actually I had one from one type and one from one signal and one from another. So now it looks like this. Is it okay? Actually, it still look okay here. Okay, so if you want to have another signal, you can actually try the second lead here. Or you can have, instead of 118, you can have 119, another patient. Okay, it looks very different. Okay, but actually still looks okay here also. Okay, So you can try, maybe I can just comment that here. Okay, so it's up to you to choose whatever signal you want. Okay, maybe I can just actually it might be better to have it here so that you can see it yourself. Okay, so basically here it's 118. It's 118. Okay, so maybe I can have also the same thing here as either it's S118 or S119, and this is leads. And here it's electron motion. Okay, and this is S119 if you want. Okay, so you can choose either this or that. Okay, C is still okay, the same, exactly the same, but actually you can choose the electrode motion here instead of the EMG. Okay, this is the zero phase filter that doesn't look good. Okay, see if, for example, if you look at this here, you can see that basically the variations here in the electrode motion actually have a baseline wonder component. Can you see that? It basically, the electrode motion has two components. It has a low frequency component and a high frequency component. If you want to see it, maybe you can just go to the original ECG demo and run it again so that we can see how it looks like. Basically, this is the EMG, I think. This is a baseline wonder, and this is probably one of the electrode motion artifacts. So the difference looks like this. So this is the error. This is the noise. It definitely has a baseline wonder component, but actually it has also an overlapping high frequency component. So for this particular type, you will probably need to apply both filters, low pass and high pass, which means that you effectively will have to use a band pass filter. Okay, so here, basically for the band pass filter, you try to estimate the low frequency, the cutoff frequency, the low cutoff frequency for the high pass filter from the baseline wonder component, and try to estimate the frequency for the low pass filter from the high frequency noise that you have here. If you want, you can apply these filters one at a time. So basically, I can take this signal, for example, as you see here, this is signal 119. Try this particular signal, 119, and basically try to remove only the component that has the low frequency, that has the baseline wonder. So basically here in this filter, this is a high pass filter, and basically instead of high pass filter, this is electrode motion high pass filter. I'm just instead of selecting the baseline wonder here, I'm going to select the electrode motion, and I'm going to select signal 119 so that we can see the same exact signal that we're looking at now. See now what happened after basically this is a signal with noise. Okay, after we did that, after we did the filtration, we removed the noise. Basically, we removed the component corresponding to the baseline wonder. Okay, so what we were looking at basically in the figure 2 here, if we okay, so Actually, basically it's overwritten here. But basically, if you compare this one to that one, you will see that basically this is actually, we came close to the original signal. We still have the high frequency noise, but the baseline wander component of electrode motion artifact has been removed. Okay, so this is a first step. After that, I can try actually to take this output signal and apply another filter. Apply basically a low pass filter so that I can remove the high frequency noise. Or I can, from the start, I can just design something that would work with a band pass filter. So I can go here, go back here. Maybe I can just go to the filter designer and just select band pass filter. Okay, and design the filter T60 cutoff frequency. Now basically you have the f-stop. Maybe you can just use the same parameter that we use for the other one, 0.5 and 1, and then I'll use the other frequency that we also used in the other one, 20 and 25. And the attenuation here, you have two attenuations in this case. You have, because you have basically two stop bands, one in the beginning and one in the end. So basically can have both as 40 decibels. Let's design that filter and see how it looks like. See how it looks like? Basically, you're talking about, actually it looks a little bit strange, because actually it's too large. You should actually have 0 here and it should go minus here. So this doesn't look right. So you start seeing some things that are not right. So basically here, 360 f-stop, this doesn't look right. So the filter wasn't designed properly here. So I'll just choose another one here, another type, because sometimes it's it fails to actually get a result, a good result. See, now it's much better. Okay, so you look at the filter and verify that it looks like the one that you expect from this filter. Sometimes the method that is used actually doesn't work. So I'll generate the filter design function, leg 5, band pass filter, FIR, electrode motion 1. Okay. So this is the function. I'm going to comment that. I'm going to take the this one here, take the whole area, everything here after, the one that has the signal and everything, and place it here. Here I just basically read the signals. Okay, I actually have, if I use 119, so we should have also that. I basically, these are the signals that I was showing you, and this is SIG-F, whatever, okay? This is exactly the same thing. Let's run that. Okay, this is true. This is actually the outcome here. The outcome, basically, this is the input versus the output. And basically, if you look at it, the one in red actually is the one that came out. The baseline one that is gone. And basically, the peaks of the ECG overlap, but there are some differences between them. Basically, if you look at this one and this one, you see that the blue one is a little bit higher. Okay, so basically it's not exactly the same, but actually we can optimize the parameters of the bandpass filter in order for us to get something that would look a little bit better. Okay, so my optimization here was to go and change the parameters here so that I can get something that would look good. The first one, the 0.5 and the 1, they seem okay because actually I don't really see any baseline variations if you see here the outcome here, you see here the baseline one that actually was very clearly having a low pass component here. Now the outcome doesn't have it. So basically, I assume that the 0.5 and the 1 are okay. Okay, so I will change the other one, the other frequencies. So maybe I can just have that as 15 and maybe 20 here and see. It's very difficult to actually compare them even here, but actually we can go back to our parameters here, the metrics here. This one is 0.0529, this is 0.0558. So if you compare these two, which one is better? Is this experiment better or the previous one? Which one of these would be better? 0.0529 or 0.0558? This is larger, right? When it's larger, the error is larger. So it's not better than the first one. Definitely the first one here was better. Okay? So basically this is exactly what you should be doing in there, in the electrode motion experiments. Basically you expect things that look a little bit less glamorous than the compared to the other ones. Basically the signals coming out will not look very good. They will definitely look noisy like this, but actually try to show improvement. So if, for example, I showed that it was looking like this in the inputs and looking like that in the output, this is a major improvement. This is definitely an improvement. Nobody will actually argue with that. So try to also basically look at some place in the signal where you have a high frequency noise and try to see if it's improved here or not. And basically, if not, you try to basically minimize the norm that you chose and just do a few experiments and just report that. Is it clear to everybody what you should be doing? Is it clear? Is it clear for you? Do you have any questions on how to do that?
For me, clear enough.
Okay. So basically, these are the experiments that we were talking about. Basically, you're going to do some more experiments, and basically, for the requirements of the research problem one, I'm going to post them later today. They will be available on Blackboard as an assignment too, and you should just basically look at them, and if you have any questions, let me know. The assignment will have basically some data. I'm going to include some data so that you can use for this particular assignment. Okay, so the assignment file will have a PDF for the actual assignment and the data for the question, the 20% question that I told you about. The remaining parts will be experiments just like the ones that we did now. Okay, for the motion artifact and for the EMG artifact, if you're going to work with the frequency domain, it's exactly the same as we did before. We just remove the range of frequencies that basically that you see that basically it's not really basic that correspond to the noise, and that's it. Okay. For the remaining part here, for the review of reporting of research results, I'm going to start with that next time because it's probably enough for you today. It's just a general informal discussion of research and how it's published and basically how reliable are the publications if you want to publish somewhere, where exactly you should go, and the difference between different journals. So we're going to discuss that inshallah next time. And I'm going to introduce the second research problem. Just give you the background of the second research problem. I'm not going to code anything next time. Just gonna be just a presentation, just give you the background of the research problem too. Do you have any questions?
And thank you.
Yes.
Okay, so if you don't have any questions, inshallah, we will meet next time. And hopefully you will hear from, actually Tariq is here. I was asking about you, Tariq.
Yes, I joined.
Okay, okay. So if you find yourself late on some of the topics in the course, just let me know. You can actually ask for office hours if you want to, so that you can catch up.
Yeah, thank you. Yeah, I think I need some support. Thank you, doctor.
Okay, good luck, inshallah. So inshallah,
Okay.
today I will post assignment 2, and please try to submit assignment 1 as soon as possible, okay? The deadline in 2 weeks for assignment 2, basically, if you need a few more days, it's fine. I'm not gonna, I don't have penalty for late submission in this course, okay? So as long as you understand what you're doing, it's fine. I'm not gonna deduct any points, okay? But I hope that you can do that, because I want you to catch up with research problem 2. I don't want any delay from research problem 1 to affect your performance in research problem 2.
Yes,
Okay.
yeah. One and research problem 1 after 2 weeks, right?
Yes, yes, yes.
About assignment, about assignment
It's
2.
assignment 1. Just send it whenever you have it, whenever you complete it. Okay.
About assignment 2.
I can't understand your voice is not clear. Can you repeat, please?
You will be submit assignment 2, right?
I'm talking about the assignment 2. The date I'm talking about is assignment 2. Yes.
Assignment 2.
Yes, yes. Please, when you get the assignment 2, please look at it. If you need more time, we can actually we will see what we can do. Okay. I don't want you to be rushed. I want you to understand what you're doing. So basically, whenever you get research problem 1, the assignment 2, basically of research problem 1, please look at it and let me know of any problems you might have in submitting the results by the 2-week period that I talked about.
In this 2 weeks, focus on assignment 1, research problem 1.
Basically, assignment 1 plus assignment 2 is research problem 1. Okay, so I divided the requirements into 2 assignments. So for the assignment 1, from what you told me, that most of you are basically, you don't really have many questions on research assignment 1, basically. So if you have any questions, let me know. Okay, try to finish as soon as possible, whenever you can. Okay.
Assignment 1 and assignment 2, or research problem enough.
I'm not sure. Can any of you understand because actually it's very difficult to. The voice is not clear. If any of the other students heard him better than I did, can you explain what he said to me? Can you write your question in the chat area?
Okay, try by points. Assignment 1, assignment 2 is probably the research 1, right?
Yes, assignment 1 plus assignment 2 is research problem 1.
Okay, can I do the problem research and that's enough? Send it to you one time.
I really can't hear you. Okay, can you please write the question here in the chat area? There's a chat area there. If you just open on your screen, there is a chat area. It has like a bubble, and you can write. I'm still waiting for the question. I'm not sure. Do we have? Can we? Yes.
Okay, Doctor, I will be sending you WhatsApp.
Okay, that's fine. Okay. Okay. So inshallah, I see you next time, and we can discuss this on WhatsApp. Inshallah. Okay.
Thank you very much.
Okay. Thank you very much. Assalamu alaikum.